All right, so let's work on this guy. So what are we looking for? We want to determine the maximum shear at C. So there's C. So I want to find the shear there. And I've got some wheel loads from a truck over here on the right. And it's going to move from right to left. And you can see the loads, 1 kilonewton, 4 kilonewtons, 6 kilonewtons, and then 1 meter and 3 meters. So we have 3 loads in our set, so we're going to have to check 3 cases. The first part of this would be to find the influence line for the shear at C. So we can use Mueller-Breslau to help us with that. So I'm looking for the shear at C. I'll go ahead and draw my template, and then we'll look at what's going to happen here. Now you might remember we're going to use our strange little shearless connector, right? And we're going to put positive shear on each side and see how this thing's going to move. So let's look at the left-hand side first. You look at this point right here at C, so it's free to move vertically, but under this positive shear load, it should move up or down. It should move down. And then the right-hand side, supported here at B, it's again free to move up or down. But with this positive shear force, it's going to move up. So it should get an influence line that looks something like that. That's the quantitative part. Now the geometry says that this is 6 meters and this is 2 meters. Now these are similar triangles, right? So this height here is to 2 meters as this height here is to 3 meters. So what I like to do is I like to look at it as, well, this is 2, this one is 3 times as big, right? So that means whatever this height is here, this one's going to be 3 times as big. So 3 plus 1 is 4. There's 4 of them. So this should be minus a quarter and positive 3/4. Remember, the sum has to be 1, right? We talked about that, yeah.
Is shear pretty much always, is shear always going to have the jump
Yes.
on each side,
Yeah.
and then moment's always going to
It's going to be continuous.
continuous?
That's because, remember, we're looking for the shear at C, and as the unit load approaches C from the left side, it's creating, and then once it jumps over, it shoots up, and that 1 is because the unit load has a value of 1. Everybody see that? I continually see errors at this point. And you'll notice there's no mathematics. It's just a thought process. So 1/4 is to 2 as 3/4 is to 6. You can see that part, right? Similar triangles. Okay, so that's it. That's half the problem and not a calculation. Well, in your head. So now we need to check all the cases. So let's start with, I'll come over here and do it up here at the top. So we'll start with case 1. So what I'll do first is I'll redraw this. You may not have to do this on the exam or for your homework, but I like to do it because I think it's kind of instructive. Oops, if I did it right, I could. Having trouble seeing my line there. Sorry about that. That got a little messy. So again, we know this is minus 1/4. This is going to be 3/4. I'll go ahead and put my dimensions on there again. 1 meter. 2 meters. And 6 meters. And now coming from the left side, we're going to bring it over and let each of these forces have a turn at the biggest influence. Now, just looking at the influence line, which of the areas is bigger? The positive or the negative? The positive. In fact, the largest ordinate value in the positive sense is 3 times as big as the negative. So there's probably no point in looking at the negative value. We're just going to look at positive values. There's always going to be bigger numbers. Right? If they were balanced, then you might have to check. But this one's pretty much heavily weighted to the positive side. So as I let each of these come across, when they get to C, I'm going to use 3/4, not -1/4. I'm going to be just to the right of C. So when I draw my first force coming in here, that's the 1 kilonewton force. It's going to be sitting right here at the top. And then 1 meter back is the 4 kilonewton force. And then 3 meters back is the biggest one, the 6 kilonewton force. So we've got to find those ordinate values. So what's the slope of this line? Well, the rise is 3/4. And what's the run? 6. So that becomes 3/24, which is 1/8. Is that right? So every meter I move to the right, I drop 1/8. So I move 1 meter to the right, and I drop 1/8. So I got 3/4, which is 6/8, minus an 1/8, which is 5/8. And then I move 3 more meters, so I should drop 3 more 8s. 5/8 minus 3/8 is 2/8. Everybody got that? So now I can calculate my shear at C. So I'd have 1 kilonewton times 3/4 plus 4 kilonewtons times 5/8 plus 6 kilonewtons times 2/8, which is really 1/4. So that's 3/4, 2.5, 3.25, and another 1.5. That's 4. 4 and 6, 4.75. I'm guessing.
I got 4.75.
I'm a good guesser. Here we go. So case 2, gotta just keep trudging along. So again, I'll redraw it so you guys can see it. So there's our influence line. And now we'll let the second hit the top of the hill, which is right there. So that's our 4 kilonewton force. And then 3 meters back is the 6 kilonewton force. And 1 meter forward is the 1 kilonewton force. I should have given myself a little more space there. So we're looking at these values. Now I already know the top of the hill here. That's 3/4. What's this value right here?
3/8.
Yeah, we're going to go back 3, and remember we're dropping an 8. So we're going to subtract 3/8 from 6/8, so we get 3/8. Now, this looks like a different rise over run, but it's going to give you the same slope. But we'll check it just the same. So the rise here, remember that was minus, this is a max of 1/4, right? So we're going to start off with a rise of 1/4 over a run of 2. And you can see you get the same slope. And this distance here is 1 meter. So 1/4 is 2/8, and you subtract an 1/8, you get an 1/8. It would be negative. So now the shear at C for this one is going to be 1 kilonewton times minus 1/8 plus 4 kilonewtons times 3/4 plus 6 kilonewtons times 3/8. Oh boy, let's see, 18, 17, 8, 3. It's 3 and 17/8.
5.125.
Or 3 and 17/8. I don't think that's right, but I threw it out there. And you can see right now that that one's the more critical one of the two. Now you could probably start thinking, maybe the third case I don't need to do. What's going to happen in the third case? Well, my biggest load is going to go up to the top of the hill. And we know there'll be 6 times 3/4. And 6 times 3/4 is 4.5. And then a bunch of negative stuff. So it'll get smaller than 4.5. So you could stop if you see that. But as my wife reminds me, I am not a smart person. So I should continue on. So I will. So I'll redraw this again. Okay, so in this scenario, now the last load is at the top of the hill, and that's our 6 kilonewton force. And then look what happens. 3 meters ahead, well, that section of the beam is only 2 meters. So everybody has left. The front 2 wheels are off the structure. So it's just that. You're done. So this will be an easy calculation. The shear at C is 6 kilonewtons times 3/4, which is 4.5. And what is the maximum of those three? Looks like case 2. So actually the solution for the maximum shear at C will be 5.125 kilonewtons. That's the maximum shear at C for that set of loads. Any questions about that? None? Okay. These are very testable, examinable problems.
I've got one question.
Oh, okay, yeah.
So on the previous problem, where we were finding the moment, after we drew our influence line, then we placed a unit load right in the middle, and then we cut the beam and found our bending moment. Why did we not have to repeat that process for the shear?
Well, shear has the, characteristic that we know when it jumps like this that it has to be 1.
Okay. All right.
And once you know that, then similar triangles will help you find those values. Moment doesn't have a cool little relationship like that.
Okay.
You've got to actually go do the statics.
Gotcha.
Okay.